Let us look next at an arbitrary function on phase space. So we have an arbitrary function f, which may depend on position coordinates, momentum coordinates, and might depend explicitly on time. This is an arbitrary function on phase space. And we'd like to understand how this function, the value of this function, evolves in time as we follow the physical trajectory. So we'd like to calculate the total time derivative of this phase space function as we move along the physical trajectory. Well, given that this function may depend on all the coordinates q and p and time, we have several contributions. We have the sum over I, partial derivative of f with respect to qi times qi dot. Then we have a similar contribution with all the partial derivatives of f with respect to the pi's, pi dot, also sum over all I. I'd like to take the sum in front of a bracket, so I'll write it in this fashion, plus, if we have an explicit time dependence, the partial derivative of f with respect to time. Now in this expression appear qi dot and pi dot, and since we follow the physical trajectory, we can use the Hamilton equations to express qi dot and pi dot as partial derivatives of the Hamilton function. So using the Hamilton equations, we write this as sum over I partial f over qi, and qi dot is given by the partial derivative of the Hamilton function with respect to pi. For the second term, pi dot is given by, remember, is given by minus the partial of h with respect to qi. So we have now a minus sign in front, partial f partial pi times partial derivative of Hamilton function with respect to qi. And we still have the partial with respect to time. Now for this first contribution, for the sum, one introduces a compact notation. One writes this as a so-called Poisson bracket. It's written like this, f, comma, h, in curly brackets. It's a so-called Poisson bracket. Plus the partial with respect to time. And this is a compact way of writing the dynamics of an arbitrary phase space function. I should tell you on the next page how exactly the Poisson bracket is defined. We have two arbitrary functions on phase space, f and g. And for these two phase space functions, we define their Poisson bracket in the following way. It's the sum over I. Then we have the partial of f, the first of these two functions, with respect to qi, times the partial of g, the second function, with respect to pi. And from this we subtract a term that looks very similar, only that Q and P are interchanged. So now we have the partial of F with respect to Pi times the partial of G with respect to Qi. And as before, in our notation, when we write, for example, the partial of F with respect to Qi, then since F is a phase-space function, it's understood that all the other Qj's, j different from I, are kept fixed, and all the momentum components are kept fixed. So keeping all other Q, let's say Qk different from I, and all Pi fixed. And likewise for all the other partial derivatives that appear in this expression. This is the definition of the Poisson bracket of two functions. The result, so the Poisson bracket itself, is again a phase-space function. So the Poisson bracket of two phase-space functions gives another phase-space function. So we state this, Fg is again a function on phase space. And we have a number of interesting properties. For the Poisson bracket. Property number one, which should be quite obvious from the definition, is that it is anti-symmetric. So if we interchange F and G, we look at the Poisson bracket of G and F. This is simply minus the Poisson bracket of F and G. Do you see that immediately from the definition? It's anti-symmetric. One consequence of that anti-symmetry is that the Poisson bracket of a function with itself is always 0. A second interesting property, if I take the Poisson bracket of a function f with a linear combination of two functions. So I have, let's say, C1 G1 plus C2 G2, where the coefficients are numbers and the G's are functions, then we find that the Poisson bracket is linear. This simply gives C1, the number C1, times the Poisson bracket of F and G1, plus the number C2 times the Poisson bracket F with G2. So it's linear. Here I wrote it as linearity in the second argument, but it's also linear in the first argument. You can simply use the first property, the anti-symmetry, and up to sign you exchange the role of first and second argument, and you see that it's also linear in the first argument. So in fact, the Poisson bracket is linear in both arguments. Property number 3, that's a bit less obvious to see. And I encourage you to check it for yourself. Maybe it will become a homework problem, maybe not, but you should check it for yourself. When you take the Poisson bracket of a function f with the product of two functions, now g and h are both functions, they are not numbers. in contrast to property number 2, where the C's were numbers. Here G and H are two functions. This is equal to the Poisson bracket of F and G times H plus G times the Poisson bracket of F and H. This is called the product rule. And it's reminiscent of the product rule that you know from differential calculus. If I take the derivative of a function, a product of two functions, it's function 1 times the derivative of function 2 plus the derivative of function 1 times function 2. That's the product rule of differential calculus. And if you consider taking the Poisson bracket with f as a kind of derivative, then you find taking the Poisson bracket of a product with f equals taking the Poisson bracket of the first factor with f times the second factor plus the first factor times the Poisson bracket with the second factor. So taking the Poisson bracket with f is a bit like taking a derivative. It gives you the same product rule. Yeah? And finally, that's perhaps the least obvious of the properties. This is a Jacobi identity for the Poisson bracket. And it reads as follows: the Poisson bracket of some function f with the Poisson bracket of G and H plus, and now we sort of exchange the arguments counterclockwise. So the Poisson bracket of G with the Poisson bracket of H and F plus the Poisson bracket of H with the Poisson bracket of F and G. This sum is equal to 0. And that is a Jacobi identity. And this will be quite certainly on your next problem set that I will ask you to prove that Jacobi identity for the Poisson bracket. I told you that the Hamiltonian formulation of classical mechanics constitutes a bridge towards quantum mechanics. And here I would like to give you a very, very brief outlook on quantum mechanics, to give you just a little idea what this relationship looks like. Perhaps some of you have recognized the Jacobi identity. That's also an identity that holds for when you take the commutator of two operators, or the commutator of two matrices. So compare this Jacobi identity for the Poisson bracket with the Jacobi identity for commutators. The commutator of two matrices, or more generally linear operators, is defined as A B minus B A. A and B are matrices, or more generally linear operators. Now the commutator satisfies a Jacobi identity. The commutator of A with the commutator of B and C plus the commutator of B with the commutator of C and A plus the commutator of C with the commutator of A and B is equal to 0. So, at least in this respect, the Poisson bracket is very similar or has the same properties as the commutator of two operators. Also, for example, the antisymmetry also holds for a commutator. The commutator of B and A is minus the commutator of A and B. So there are a lot of similarities and parallels between Poisson brackets and commutators. Now, in quantum mechanics, what happens? You learn that, I guess most of you will learn that next semester. In quantum mechanics, you no longer have phase-space functions, but instead, observables, physical observables, are represented by operators. Classical mechanics lives in phase space, and physical quantities are represented by functions on phase space. Quantum mechanics lives in so-called Hilbert space, and physical observables are represented by operators in Hilbert space. And the Poisson bracket between two observables in classical mechanics are replaced in quantum mechanics by 1 over I and then Planck's constant h bar and the commutator between operators. And this is actually a simple so-called quantization rule. If you know the properties of a system in classical mechanics, you know the Poisson brackets, and you want to describe that quantum mechanically, then the quantization rule is that you replace the Poisson bracket by the commutator between operators. That's just a brief outlook. Maybe it makes you a bit curious also, and makes you look forward to quantum mechanics. And it illustrates one of the aspects where Hamiltonian mechanics is sort of as close as possible to quantum mechanics. As for the Poisson brackets, let's have a look at a few particularly important cases. Let's look first at the Poisson bracket of Qi and Qk. Or you may view the position coordinates as phase space functions. They are very simple functions. The function Qi on phase space just returns to me the value of the coordinate Qi. It assigns to every point in phase space its coordinate Qi. So it's a phase space function. And so it's totally legitimate to look at the Poisson bracket between two such functions, Qi and Qk. Let's look at the definition. Now we need a different summation index because I is already taken. So let's have as a summation index J. Then we have the partial Qi with respect to Qj, partial Qk with respect to Pj, minus, and now with Q and P in the denominator interchanged, so we have partial P, J, and then partial Qk, partial Qj. When we look at the partial derivative of Qk with respect to Pj, keeping all the Q's fixed, this is 0. Likewise, the partial of qi with respect to pj, keeping all the q's fixed, this is 0. So in fact, this Poisson bracket equals 0. And this is the first of the so-called fundamental Poisson brackets. The Poisson bracket of two position coordinates is 0. Let's look at the Poisson bracket of two momentum coordinates, momentum components, pi and pk. It's a very similar argument. Again, it will turn out to be 0 because in here you have the partial derivative of pi with respect to qj. And already you recognize, for the same reason, this is equal to 0. And then you have minus the partial of pi with respect to pj, partial pk with respect to qj. Again, this partial is 0, and therefore both terms vanish and the Poisson bracket is equal to 0. This is the second so-called fundamental Poisson bracket. There's a third fundamental Poisson bracket, and finally that's the one that does not vanish. We can look at the Poisson bracket of a position component with the momentum component, so qi pk. We have partial qi qj, partial pk qj, minus partial qi pj pk qj. Now, first of all, these mixed terms here, partial q with respect to p or partial p with respect to q, these vanish for the same reason as before. But the first contribution does not necessarily vanish. We have the partial derivative of qi with respect to qj, keeping all q's fixed except for qj. Now this is 0 if I and j are different, but this is 1 if I and j are equal. So it's a Kronecker delta. It's a delta ij. And likewise for the partial of pk with respect to pj. Oh, I realize I misspelled here. This is a pj. Sorry. This is 0 if k and j are different, and it's 1 if they are equal. So it's also Kronecker delta jk. We can simply perform the summation over j, and with the Kronecker deltas, this gives us delta ik. This is the third and last of the fundamental Poisson brackets. You have questions about this calculation? Is that clear how we get there? Yeah? So these are also very important, very basic in Hamiltonian mechanics. The fundamental Poisson brackets between the Q's and the P's. As the last topic in the context of Poisson brackets, I would like to reconsider the Hamilton equations of motion. They can now be written in a very compact way, simply as qi dot equals the Poisson bracket of qi with the Hamilton function, and pi dot is the Poisson bracket of pi with the Hamilton function. These are, of course, special cases of the more general relationship that we had found here, that the time derivative, the total time derivative of an arbitrary phase-space function is given by the Poisson bracket of that phase-space function with the Hamilton function, plus possibly the partial time derivative. If for the phase-space function f we use qi or pi, we get immediately the Hamilton equations written with Poisson brackets. Next, I would like to go one further step in the level of abstraction, and I would like to consider a vector with components qi, q1, q2, and so on up to qf, and then p1, p2 up to pf. This is a 2f dimensional vector, and the components of that vector are the coordinates in phase space. And I'd like to give this 2f dimensional vector a new symbol. I call it the vector pi. And this is the, if you wish, the position vector, in quotation marks, the position vector in phase space. Yeah? So I'd like to move away from q's and p's and simply talk about coordinates in phase space, whatever they are. I have 2f coordinates in phase space. I know I'm not quite done with Poisson brackets yet, because now I would like to look at the Poisson bracket of component pi I with component pi j, where I and j can take values between 1 and 2f. I define this Poisson bracket as, if I go through all the possible values for I and j, I get a 2f by 2f matrix with components a, I, j. So A is a 2f by 2f matrix. What does that matrix look like? I can divide it into 4 submatrices. Each submatrix is an f by f matrix. Now let's look at the top left submatrix. In there you have, for example, the Poisson bracket of pi 1 and pi f, for example. Now pi 1 is q1, pi f is qf. The Poisson bracket between two q's is 0. That's one of the fundamental Poisson brackets. In fact, in this top left corner, top left submatrix, you have all the Poisson brackets between the q's, because the first f components of this vector pi are just the q's. But the Poisson brackets between the q's are all 0. So this is in fact all 0 in the top left. Likewise, in the bottom right, you have all the Poisson brackets between the different p's, because the components pi f plus 1 and higher up to pi 2f, that's what you have on the bottom right. These are all the p's, and the Poisson brackets of the p's amongst themselves all vanish. So this is also 0. And then let's look at, for example, let's look at this one here, which would be the component A1 f plus 1. Okay? So it's within this submatrix, top right, it's the entry in the first line and the first column, first row and first column. Now what is that? That's the Poisson bracket between pi 1 and pi f plus 1. But pi f plus 1, the f plus 1th component of pi is p1. So in this yellow cell we have the Poisson bracket between q1 and p1. But this is again one of the fundamental Poisson brackets, and that's equal to 1. So that entry is a 1. Likewise, you will find if you go down the diagonal of that submatrix. So the next entry on the diagonal will be the Poisson bracket between pi 2 and pi f plus 2. Pi 2 is q2, pi f plus 2 is p2. The Poisson bracket of q2 and p2 is 1. So you will see that on the diagonal you have all 1s. On the off diagonal, you have, for example, the Poisson bracket between, say, pi 2 and pi f plus 3. That equals the Poisson bracket of q2 with p3. But this is 0 because the indices are different. So off the diagonal, it's all 0, and on the diagonal, it's all 1. So in fact, the submatrix in the top right is the f by f unit matrix. Now we still need the submatrix bottom left. Again, you might look at the entry, say this one here, first row, first column of this submatrix. That would be the Poisson bracket of pi f plus 1 with pi 1. Now pi f plus 1 is p1, pi 1 is q1, so in there you have the Poisson bracket of p1 with q1. The Poisson bracket of p1 and q1 by anti-symmetry is minus the Poisson bracket of q1 and p1. The Poisson bracket of q1 and p1 is 1. So in this yellow cell you have minus 1. And with this, in the same logic as above, you find that on the diagonal of that submatrix, it's all minus 1. And off the diagonal, it's all 0. So in fact, the lower left submatrix is minus the f by f unit matrix. Now, next, we look at the Poisson bracket of two arbitrary phase-space functions. You know how this Poisson bracket is defined with the qi's and the pi's. And now I would like to write this Poisson bracket in terms of the pi's. And I give it to indicate that, I give the Poisson bracket a little subscript little pi. And I claim that I can write this Poisson bracket in the following form. It's the sum over all I and j, both indices going from 1 to 2f. Then I have the matrix element aij, where this comes from this matrix A that we were just looking at. And then I have the partial derivative of f with respect to pi I. And I have the partial of g with respect to pi j. Would you like me to show that to you, that this is this form? Yeah, I'm happy to do that, and I'll do that on a separate page. So this is about the Poisson bracket with phase-space coordinates. So this is the claim that the Poisson bracket between f and g, that's the sum ij going from 1 to 2f, aij partial f partial pi, pi I, partial g partial pi j. I can divide this up into two sums. I can first take the sum I going from 1 to f and j going from 1 to 2f, aij partial f partial pi partial g partial pi j. And then I take the second half of the sum I going from f plus 1 to 2f and j going from 1 to 2f, aij partial f partial pi I partial f g, sorry, partial g partial pi j. Now, if I is between 1 and f, then pi I equals qi. Now we have in front of these partial derivatives, we have these matrix coefficients aij. If you remember the shape of that matrix, then given I, so given a row I, in this ith row, there's just a single entry which is non-zero. Let's look at this matrix again. We are now in the case where I goes from 1 to f. So we are talking about the top half of this matrix. We look at the ith row, and in the ith row there's just a single entry which is non-zero. It's in fact 1, and it's the entry in the I plus f column. So the sum over j collapses, only a single j contributes, namely the j which is equal to I plus f. When j is equal to I plus f, then the pi j, so the pi I plus f, that's the momentum component pi. So the I plus f component of the vector pi is the component pi of the momentum. So, in fact, this first half here, what remains, what survives, is the sum I going from 1 to f, partial f, partial qi, partial g, partial pi. Then let's look at the second contribution. Here I goes from f plus 1 to 2f. So we are now in the lower half of the matrix A. Pi I is then, we can do the following, we can, rather than saying I goes from f plus 1 to 2f, then the pi i's are momentum components. Okay? And we can introduce a new summation index, say k. K goes from 1 to f, and we replace I by f plus k, and pi f plus k is then equal to the momentum component pk. Then same logic as before. Given a row of this matrix A, there's just a single entry which is non-zero. In the lower half, this single entry is minus 1. So this becomes minus 1. The sum over j collapses. And the only j that contributes is, if we have f plus k, if we have the f plus kth row, then the only column that contributes, where the entry is minus 1, is the kth column. And in this kth column, and then here we have qk. So pi f plus k, pi k, is equal to qk. Oh, this is really, one really has to be awake. Okay. So what remains here from the second sum, with a minus in front, we have a sum k going from 1 to f. Then we have a partial f partial pk times partial g partial qk. And now in the second sum, you can now relabel summation indices. You can replace the k by an I again, take the two sums together, and then you have sum over I from 1 to f, partial f qi, partial g pi, minus partial f pi, partial g qi, and this is the familiar definition of the Poisson bracket. So let's return to the previous page and take it as a given now that we can write the Poisson bracket in this new form. Next, we look at coordinate transformations in phase space, no longer just limited to configuration space, but in phase space. And the idea is that we go from the phase space coordinates little pi to new coordinates, which I call capital Pi. And the new coordinates are functions of the old coordinates. So we have some transformation rule that relates the new coordinates to the old coordinates, and possibly this coordinate transformation is time dependent. So there might be a time dependence in this coordinate transformation. So, for example, the original position components, little q, become new position coordinates, capital Q. But now the key difference is to the previous coordinate transformations that we considered, that this new position coordinate, capital Q, may depend not only on the old coordinate, little q, but it may also depend on momentum, the old momentum, p, and may depend on time. So these coordinate transformations in phase space, they can mix up position and momentum coordinates, components. Yeah? And likewise, the momentum, the old momentum, little p, may become a new momentum, capital P, which may depend on the old positions, momenta, and possibly time. Yeah? So we allow arbitrary coordinate transformations in phase space where the new coordinates may be an arbitrary function of the old coordinates, and this implies that we possibly mix up positions and momenta. Associated with this coordinate transformation is a Jacobian matrix. That's the matrix of partial derivatives of the old coordinates, little pi, with respect to the new coordinates, capital Pi. This is the Jacobian. Up to this point, these are really general transformations, and now I would like to single out a special class of transformations which are called canonical, and they are particularly important in Hamiltonian mechanics. Let's now look at the Poisson bracket of two phase-space coordinates, the old phase-space coordinates, little pi, k, with pi, little pi, l. We know, now if we evaluate this Poisson bracket by taking the partial derivatives with respect to the little pi's, then we get on the right-hand side the AKL, this A matrix. Look at this here. You have the Poisson bracket between pi I and pi j equals the Aij, with the matrix A given as up there on the right-hand side. Here, when we calculated the Poisson bracket, we took the partial derivatives with respect to the original coordinates, so the little q's and the little p's. Here I would like to do something else. I would like to evaluate this Poisson bracket by taking the partial derivatives with respect to the new coordinates, the capital pi's. So this is the Poisson bracket of the old coordinates evaluated in the new coordinates. So if we take our new way of writing the Poisson bracket, it's a double sum ij going from 1 to 2f. Then we have the matrix component Aij, and then we have the partial of the first function, which in this case is little pi k, with respect to the phase space coordinate, and here we want to use the new coordinates. So we have the partial with respect to the capital pi I, and then we have the partial of the second argument of the Poisson bracket, which is our old coordinate little pi L, with respect to the new phase space coordinate capital pi J. The first partial derivative that appears in here is by definition the component ik of the Jacobian. The second partial derivative is by definition the component jl of the Jacobian. So in fact we have here in the sum represents a product of matrices. And we can write this as the KL component of the matrix product of the transpose of the Jacobian times the matrix A that we had defined on the previous page times, once again, the Jacobian. This here, this is nothing but the ik component of the Jacobian is the same as the ki component of the transpose of the Jacobian. And then if you read it in a different order, then you have a double sum transpose of the Jacobian ki times a ij times Jacobian jl. And then it's easier to see that it's a matrix product of three matrices in this order. Transpose of the Jacobian times A times Jacobian. And of this, the KL component. This implies that the Poisson bracket of the original coordinates, the little pi's, evaluated in the new coordinates, the capital pi's, that these Poisson brackets equal the original Poisson brackets, which were the Poisson brackets of the original coordinates evaluated in the original coordinates, which were equal to the AKL, these matrix elements, if and only if this matrix product, transpose of the Jacobian times A times Jacobian, that if this equals A. Yeah? If this condition is satisfied, if the Jacobian of the coordinate transformation satisfies this condition in the box, inside the box, then the Poisson brackets of the phase space coordinates are the same in the old coordinates and in the new coordinates. And then the Poisson brackets are invariant under coordinate transformation. Now, phase space, coordinate transformations in phase space, which have this property, whose Jacobian has this property, so that the Poisson brackets are invariant. These are particularly important, and these are the so-called canonical transformations. So this is the definition, phase space coordinate transformations whose Jacobian satisfies this property are called canonical. I realize this is a bit abstract. You'll have, on the next problem set, you will have an example of a canonical transformation to make it a bit more tangible, a bit more concrete. And we will see, as we develop the theory further, we will realize how important these canonical transformations are. For example, one of the results that we will find maybe next week or the week after, we will soon arrive there, is that you can view the time evolution of a mechanical system as a time-dependent canonical transformation.